Hello, welcome. Now let's try to solve another Leetcode problem, 1136, parallel courses. Yeah, actually this problem is very easy to understand because it's very similar to the common life. While we are choosing a course, there's a pre prerequisite. For example, the course 3 is if you were to finish course 3, you must finish course 1 first. And you also need to analyze what is the least semesters you can choose. For example, for this one, you can first finish 1 and 2. It will cost 1 semester. And for the second semester, you can fill that costs 3. So in total, it's going to be 2, and 2 will be the minimum. Yeah. So this is why this problem is more like a template problem, and it is really easy to understand, and you can try to practice topological sort by using this kind of problems, because it is not so difficult to understand. You just need to analyze what is the meaning of this relations and what is this n and what is the meaning of the result, and then you can start coding. But you need to analyze how can you make the minimum semesters. So it is a greedy idea. If it is possible, you want to finish all the courses, as many as possible. For example, course 1 to 2. If you only finish course 1, for the next semester you have to finish course 2, and for the third semester you're gonna finish this course 3 because 1 and 2 already be finished. But for the greedy idea is you want to finish course 1 and 2 together in semester 1. Then, if you go to semester 2, you can finish this 3 immediately because there's no limit. So this is why the problem is easier. Because for each semester, there's no limit of how many courses you can choose. So the only limitation is about the sequence. You have to finish like a topological structure. Now let's just start coding. I think the explanation is enough. So this n is 5,000. It seems we can use a topological sort to solve it. Let's check the number of answers. The relations is also not a big number. So this means the time complexity would be like ON, or this 5,000 plus 5,000. It's gonna be O n plus m. If this is n, this is m. It means we can solve it by topological sort. Now let's start the coding. I'm gonna prepare a graph and integrate because I'm gonna use a topological sort BFS structure to solve it because this is more easy to understand. So for the graph, I'm gonna prepare a default dict. Inside it gonna be a list. And for this one, I'm gonna prepare an array because the number of the vertices is fixed. So for example, the number of vertices is 3. But the starting of the vertex is from 1. It's not starting from 0. So we're gonna do some trick about this kind of structure. Now I can prepare for the relationships. So let me just use the U and V in relations. So for this G, if I were to finish the course V, I have to finish the course U. So the G U should append this way. This is the sequence, right? So for example, 1 and 3 inside, I have to finish 1 and then go to 3. So this is for G. And for the integrate, it's gonna be so for the integrate inside, it's gonna be V plus 1. Now I can prepare a result. I will also prepare a count. And I think I also need to prepare a Q. So the result would be started from 0, and the count is also 0. So what's the meaning? So this result is my final result. How many semesters do I need? And this count is just to check how many courses did I finish. For example, if I only use 2 semesters but I didn't finish didn't finish 3 courses, if I only finish 2 courses, it's gonna still be a wrong. Yeah. If I want to get these 2 semesters, I have to make sure I finish all the courses. Yeah. So this is why this code is used for checking if I finish all the courses or not. Yeah, because if I didn't finish all the courses, I'm gonna return a -1. So for this example, because it is a loop. For the topological structure, it is always solve the DAG problem. It means the directed acyclic graph problem. So this graph is a cycle, so we can not use the topological sort to solve it. So that is why we're gonna return a -1. Yeah, but the topological sort can find this structure. Normally, it will not execute. Yeah, and for the queue, similarly, I'm gonna prepare the queue. I think it doesn't matter, but yeah, I will just prepare a double-edit queue. So for I for ID in enumerate in degree if this D equal to 0. So this is my starting point. So from the beginning, I'm sure there would be some node inside of the queue. So I'm gonna check this queue. While I'm checking this queue, the result is check how many semesters. Yeah. So the result should plus equal to 1. Because there's some node inside, it means at least I need 1 semester to finish those kind of courses inside the queue. Now I need to check all the courses inside the queue. Yeah, I have to use this kind of structure because this is the semester I need to check. I have to use the structure like for I in reads less of the queue because it must be layered one layer by another layer for the BFS because I need to check this result. Yeah, but for here, I can pop out the node. It should be q dot pop left, and the code should plus 1. So this is why I prepare this code. This code is just to check the total number of courses I took, and this result is the number of semesters I took. Now I can use the neighbors inside the graph, and this is the node, right? Yeah, and the integrate should check this neighbor. If I take 1, it should -1. And now I need to check if it is 0 or not. If this neighbor is 0, it means I need to put it inside the queue. Put this neighbor inside the queue. Yeah. Finally, I need to return this result if the result should be more than 0. Because from the beginning, it is 0. If I didn't execute, the result would be 0. If it is 0, it means I cannot took any courses. I cannot finish it. I'm gonna return a -1. Yeah. If it is, I still need to check this count equal to the number of courses n. Yeah. Else, I'm gonna return a -1. So here is if I would to return the result, it must be more than 0, and the count number of courses should be equal to n. It means I finished all the courses, and it took me the result, for example, is 2 semesters. Yeah. But for here, I suddenly find I did something wrong from the initialization of the graph, because the graph is starting from 1, not 0. So I needed to do some preparations for here. It should be gu -1 append v -1. So this means it's gonna just start from index 0, not from 1. Yeah. Yeah. Otherwise, I'm gonna have the index out of the limit, out of the ranges. Yeah, because basically for this in degree, I prepared the node from 0 to n-1. So this is why I have to prepare something like this. And now let me just run it to check if there's any mistakes. It seems okay. Yeah. Now let me submit it. Yeah, as you can see, it works and it's pretty fast. Now let's analyze the time complexity. And for here, first inside of the relations, I need to check the length of the relations. So it is 5,000, and for uh, each relations I, it's gonna be a number of 2. So it means 2 times 5,000, or it is just we can use this 5,000. So this is 5,000 is n. We can use on. And for this q here, this is also on. And let's check the BFS. So for the BFS, we're gonna check the graph structure. It is basically O E plus B. V is the number of vertices, E is the number of edges. Let's check how many edges. The number of edges is dependent on the relations. And the vertices is n. So the time complexity is still On. Because the number of edges is just 5,000, and the number of vertices is also 5,000. So E plus V, 5,000 plus 5,000, it is 10,000. So basically, we're gonna use On to represent the time complexity for this question. Thank you. See you next time.